Hey guys, it's time to take our progress with the Ultra96 and drive an external pin, making additions to what we have thus far. So in this video, we'll go through and create a new Vivado project, draw up some Verilog code, and make all the proper connections to drive an external pin. So let's get started. So unfortunately, the Ultra96 has a very low voltage output and it doesn't have much current to offer. So we'll have to make the actual LED connection via a transistor, which we may do in a separate video. So the first thing I want to do is go ahead and open up Vivado. It takes forever to load. It takes forever to load. Okay, so we're going to go ahead and click on Create Project, and then we'll go and hit Next. We're going to give our project a name. I'll call this U96 Blink. Click on Next. We don't want to specify our sources at this time, but we do want an RTL project. Next. So we'll go through and pick the board. If you don't have the proper board on here, then you might want to go check out my previous spin-up video with the Ultra96 that shows how to install the board file. So I'll go down and find the Ultra96 V2 evaluation platform, then click Next and finish. So what I'm actually going to do with this is follow the base project design for the very start. Unfortunately, the way this is designed, there isn't a real immediate clock into the PL, so we're going to have to use the PS as PL. So if you want to know how to do the base design, see the previous video, and I'll link that down below as well. So creating a block design, we'll go through and add IP. We're going to put the zinc down, and for this, we'll go ahead and run the block automation and click OK. And I actually want to zoom out on this guy a little bit. Now we're just going to go ahead and connect our clock pins as needed. Now from here, the base project takes you to validating the design, then generating bitstream and all that stuff. But we want to add our Verilog RTL here. So what we're going to do is add a source. We're going to add or create design sources and click on Next. Create a file. Let's call this Blink. Click OK. Click on Finish. Now we'll add an input for the clock because we're going to need a clock to blink something because it's changing in time. And then we'll add LED, and we're going to make that one an output. Now while that's creating, you might ask yourself, why aren't I using the onboard LEDs? Well, it's not apparent to me that there's a direct connection between the PL and the onboard LEDs. There may be, but this is just easier for me in the long run. We'll use the onboard LEDs when we go through and do the processor blink. So now that we've done that, we can go to sources. We've got our blink file here, and it should be completely empty except for our inputs and outputs. And what we're going to do is just create a blink code here. So we'll make a counter register. Let's call this 27 down to 0. We'll call it a counter. Then we're going to do an always block. Always at the positive edge of the clock, which obviously you don't have to use. You can use the negative edge if you like. Then we'll begin that block. Then we'll just do counter. Takes counter plus 1 at every positive edge. And then we'll end that block. And then what we want to do is assign our LED to the 27th bit of the counter register. So we can say counter 27 and make sure that you spell right. Now let's save this code, and then we're going to save our block design. Now when this is done saying updating here, we'll go back to our diagram, and what we want to do is go to sources and right click on blink, go down to add module to block design. Now we've added that module to the block design, and what we have here is a clock to run this blinky LED. Now, if you didn't do it this way, you can use block automation and stuff, but you'll still have to have the PS as far as I can tell in order to get a clock. So what I'm doing is just running this clock signal into the clock of the RTL. And now I want to go through and make an output, right? So I'm going to right click, go down to create port, and I'm going to name this port uppercase LED instead of lowercase LED. And I'll put, make it an output and click OK. Now we've got our output. What we can do is just run this directly to the LED. Now what we want to do is we want to make sure the pin that we want to use for this LED, which I've decided is going to be, I guess, pin 3 or D7. Pin 3 on the low speed bus, or D7. So what we want to do is find that pin and how it's physically connected in the FPGA. So what I'll do is I'll open up the browser and take you to this page, and I'll put this link down below. So what you want to do is find the actual header, the low speed header. So we'll go through these names over here. We got block diagram, USB, bank 0, switches, and it's not exactly apparent over here in the side, though it may be one of these guys, right? So like expansion headers or something like that. So I'm just going to scroll down until I see what looks like our expansion headers. We have low speed and high speed. There's bank 65. There's JTAG headers, bank power and decoupling, USB ports, more expansion headers. Oh, here we go. So we have 40 pin low speed expansion header. So I want to use pin number 3 here, which is HDGPIO 0. So what I can do is go through and type Control F. That'll bring up the find menu. And I can type in HD underscore GPIO underscore 0 as it was listed on that one. And what it does is brings me back over to this bank 26. And this bank 26, I have to guess, is directly off the FPGA. And if we follow this HD GPIO 0 into here, we see that that's D7. So now we know the pin that we need. What we can do is just go through and make an HDL wrapper. So you're going to right-click on the board design file and click on Create HDL Wrapper. Let Vivado manage the wrapper. And wait. Now from here, you're going to go to Open Elaborated Design. Now this takes a while. Click on that, click OK, and prepare for the ultimate wait. Now, if you run into an error on Open Elaborated Design, it's likely because you named something wrong. I'd run into some errors where I'd named LED caps in one where it was supposed to be lowercase and lowercase in the other. My actual Verilog file had a lowercase LED and an uppercase LED, and I just ran into all sorts of errors, and it took me forever to find it because it wasn't apparent. So go through and make sure that you follow things exactly. Make sure that all your names line up. Where you're supposed to have lowercase LED, you have lowercase LED. Where you're supposed to have uppercase LED, you have uppercase LED. So from here, what we can do is go up to this window and go down to I/O ports, and that'll open up these I/O ports down here. Now, we only have one named, and that's going to be our LED here. I'm not sure why it doesn't put the name over here for me in the actual box, but if you let it hover over, it'll tell you that that's the LED. So what we're going to do is go over here and go to Package Pin. That pin that we found, which was D7 from the documents that I linked down below, we're going to pick that. And then we'll go through and change this to LVCMOS 1.8 because we've got a 1.8 volt device here. Everything else should work fine. So from here, what we can do, we'll go ahead and save, and that'll force the creation of a constraints file or a pins list. So I'm just going to call it pins, and we'll click OK. We'll let that save, and then we can go through and run our synthesis. So I'm going to go ahead and run that. I'm going to use all my core power, so it may shut down OBS. And what you want to do is watch up here on the right-hand side, as we showed before, until this is done and says that it's ready. And we wait some more. So now that synthesis is completed, we can go ahead and run implementation and launch it on as many cores as we'd like. Yet again, we will wait. Okay, and from here, we generate bitstream. Click OK. Same gig. And wait just a little while longer. Okay, now that we finally have our bitstream created, I'm going to go ahead and hit cancel on this. Then we'll go up to File, Export, and we're going to export our hardware for SDK to use. Make sure that Include Bitstream is selected. Click OK, and that actually happens right away. So then we'll go File, Launch SDK, and we're going to pull from our location, from our local project. Okay, with that open, we're going to go through and build just like we did with the base project. So let's go ahead and minimize this. What we're going to need is a new board support package, and then we want to make sure that it's a standalone, and we'll click Finish. And then in here, we're going to go into our standalone, and we're going to change this to PSU UART1, and we're going to change this other one to PSU UART1 as well. Click on OK, and let that build. With these, it's best to leave the console open so you can tell when it's done. Okay, now that that's finished, we can go through and make just any program really that will run the clock. We'll go ahead and stick with the Hello World program that we had done before, because one way or another it will run that clock. Make sure that we click on Use Existing Standalone BSP so that it doesn't make its own. Click Next. Make sure we got Hello World selected. Click Finish. And then you want to let that build. The build looks like it's already done. So now we should be ready to go. I'll go ahead and get the Ultra96 hooked up so you can at least see the lights working to see that it's programming and get used to that. and I'll put a camera on it, and we'll get this thing uploaded. Okay, so now we've got our board hooked up. I'm going to go ahead and plug it in, and then I'll hit this button down here, the power button, the P4, I think. And that'll bring up all the normal lights that are programming. Make sure that those switches are in the JTAG program selection, which are both left, I think. Now we can go up to Xilinx, and we want to program FPGA, and it should auto detect, so we'll just click on program. And you want to watch those lights on the board. See, the blue one on the right went over to the blue one on the left. That means it's programmed. Now what we can do is go through and click on the HW project, go to Run, Run As, Launch on Hardware System Debugger. We're going to let that build through, and it should be running just like that. So let me take you to a view of my oscope so that we can see this up and running. Okay, so I've got this hooked up to my Rigol MSO 2027A, and you'll notice that it's flopping back and forth, but it looks like it's taking a really long time. The idea of that is so that we can actually see the LED turn on and off. So you're going to have to zoom right in on the time scale so that we can see roughly a second in total time. We'll give it a second to catch up, and you'll see it'll draw it out. So that pin is actually turning on and off. Like I said, it's just a 1.8 volt pin. We could probably figure out a way to drive an LED, but I'd feel safer running, through a MOSFET or a BJT or something like that. So I'll set up a separate video, kind of an individual content of how to drive LEDs from something with a smaller voltage and lighter current. A lot of people call this level shifting. To me, it's not technically level shifting, because if I'm level shifting, I'm going from like TTL to CMOS, or I'm going from one chip voltage to another chip voltage. For this, we're going to need to power shift, if you will, because we're going to need all the current that we need, and we're going to need all the power that we need to drive an LED. And if you do it that way, then ultimately you'll be able to drive as many LEDs as you want, as long as your power supply and all that other stuff can handle it. So keep an eye out for that video. It'll be coming up shortly. Don't forget to like, share, subscribe. Guys, keep up with me. Hit that notification bell if you want to know what's going on. Have a great day, and don't forget to love well.